Awesome. All right. So welcome everybody. Today is our great pleasure to have Professor Mingyan Liu to give us a talk titled Using Modern Machine Learning Tools to Enhance Internet Measurement and Data Processing, 3 case studies. Let me give a brief introduction of Professor Liu. Professor Liu is currently the Alice L. Hunt Collegiate Professor of Engineering and the Associate Dean for Academic Affairs of the College of Engineering at the University of Michigan, Ann Arbor. She got her PhD degree from the University of Maryland back in 2000 and has been with University of Michigan ever since. From 2018 to 2023, she was the Peter and Evelyn Fuess Chair of Electrical and Computer Engineering at U of M. Professor Liu is a well-known researcher, especially in the fields of computer networking and optimization. Her research spans quite many fields, including optimal resource allocation, performance modeling, sequential decision and learning theory, game theory, and incentive mechanisms, with particular applications to large-scale network systems, cybersecurity, and cyber risk quantification. And Professor Liu is also a fellow of IEEE and a member of the ACM. Besides the peripheral research achievement, Professor Liu is also a very successful entrepreneur. So without further ado, let's give the floor to Professor Liu.
Thank you, Mi, for that kind introduction, and hello to everybody who joined. Thank you for coming. It's a great pleasure for me to share with you some of our recent studies on the subject. And I have to say, this is the first time I'm actually combining a few different studies into the same talk. Let's see how it goes. The results, of course, done by a team of students, and I want to highlight Dr. Armin Sorabi, who was my PhD student, who is now a research scientist, and he was one who actually led a lot of the hands-on work. Okay, so what am I talking about today? The subject centers on this notion of scanning, internet scanning, and this is what I mean by internet measurements. For those of who are not familiar with the concept of scanning, I'll just say that it is the bedrock of cyber risk quantification, and I'll get a lot more into what we do with them. This is a common technique we use to essentially map the internet across thousands of ports over millions and millions of IP addresses, devices that are on the open internet. What it does is it provides us with a wealth of information on any discoverable host on a public internet, and they review how systems, services, softwares are configured. By taking this type of measurement, you know what kind of services they run, what version that software is, and how it's being configured. And it's often through that type of information we can then start quantifying cybersecurity risks. Some well-known ports, for instance, HTTP, you find out whether the device is running a web service. And if it does, you can find out whether it has a valid certificate, that's port 443, and so on and so forth. Now, if you're wondering, again, for those who, most of you here probably have taken Networking 101, but if you haven't, the fundamental reason why the internet is actually measurable, scannable to begin with is because in order to communicate, a host is always ready to receive incoming requests, right? And they're always openly listening on these ports. So if you send a query to those ports, you're going to get some response. Sometimes it's a proper packet, sometimes it's silence, and the silence itself is conveying information. So this is what we mean by scanning. Now, why do these ports exist? Ports are essentially used by system processes to provide services, and each physical device will have thousands of ports. A host is always listening, like I said, on each open port, ready to execute a particular client-server application, like incoming request to view a web page or incoming request to establish a TCP connection. And so when we say scan, we mean going to each discoverable IP addresses, and for each IP address, you send a probe to each of the port numbers. So this is what we mean by scan. Okay. All right. So with that, there are two most commonly used scanning tools, starting with Nmap, dating back to 1997. This was the original open source tool to discover hosts and their services. And again, like I said, the typical way you do that is to send packets to them, and then you analyze how it's what the response looks like by examining the headers. The reason why we say this type of scanning conveys a wealth of information is because, for instance, some services should no longer be used. Telnet, does anybody remember Telnet? We should not be continue to hear about Telnet. FTP, these have been deemed outdated and insecure, but plenty of devices continue to use these services, and so that's the one type of information you get. The other, for instance, another types of example are services that should no longer be visible to the public internet. If you're behind a firewall on VPN, that's okay. You may be able to see these services, but I should not be able to see whether these services are there on the OSU network. And that includes remote desktop, MySQL, and so on. A faster and more modern version of this was made in 2013, and that's the ZMap tool. It's actually done by a colleague here at Michigan, Alex Haldeman's group. It's a faster and more random alternative. So given a 1 gigabit bandwidth, this thing it's another open source code, can scan the entire IPv4 address space in under an hour. And if you have a higher bandwidth, you can do it faster. The randomness here is just so that you are not straining the incoming bandwidth of a particular destination network. So you don't go by the address space sequentially. You probe different parts of the address space randomly. So you spread out that bandwidth consumption. And for those who are interested, these are open source tools. You can go and download them and actually try it out yourself. Of course, the minute you start scanning, you might start getting cease and desist notices from companies that are being scanned, and occasionally we get visits from the FBI agents. I have actually met with one of them, and that's an interesting story. Happy to share offline. Okay, so that's kind of just a quick few-minute background on the basic tools we use and the type of information we collect. Okay, so what I'm going to do next is I'll spend another few minutes to show you a major exercise we did in the past, and that also has to do with our entrepreneurial effort, to highlight what is it you can do with this type of data. And then I will step through 3 more recent case studies that uses more advanced learning tools. So this past exercise used sometimes people call shallow learning tools. It was way before the emergence of ChatGPT, let's just put it that way. And no deep neural nets involved. So, okay. All right, so what we did, this was an exercise we did between 2012 and 2014. It's on risk quantification and using that to essentially predict material data breaches. So what did we do? We basically pieced together 2 types of data. One is this port configuration, which I just mentioned. So this is the data you directly get from internet scans. You discover what software, what services reside on that host, and how they are configured. And the point of that is then you can inspect and analyze the degree of misconfiguration and mismanagement. A very good example, like I said, is some services should not be visible from the public internet. So you'd be surprised to know that many printers are discoverable on the open internet. And many of these printers, their passwords have never been updated from their manufacturer's default password. And so essentially somebody from the other end of the world can basically start printing on these printers, right? And another more serious misconfiguration is running a web service without a signed and valid non-expired HTTPS certificate. Okay, so that's another very common misconfiguration, mismanagement problem. Now, if you think about this type of data, they're scalable and global because when you do scanning, it's global. When you think about their relationship to cyber incidents, okay, data breaches, and it's clear that the relationship is non-causal. It's correlational. But we are doing prediction, not causal inference. And one thing I will say is what you find is a lot of these data types are highly correlated with the thing that you're interested in. All right, so we combine this is type 1 data, we combine with a second type of data, which is RBLs, reputational blacklists. For those who are familiar with the term, these are essentially daily listings composed by organizations that have these internet sensors placed around the world on the global internet that filters through traffic to detect spam, phishing, and illegal scanning. Okay, now, and what these lists does is it contains basically unique IP addresses that have been seen to have engaged in these malicious activities. These are the types of activities that are explicit signs of botnet. To give you an example, some of you may have experienced the following. You're trying to send an email, you get an automated bounce back message that says the email cannot go out because the address on which you're sending this email has been blacklisted. Okay, so this is essentially a sign that somebody somewhere has compromised some machine, not necessarily yours, but at some point in the past, they used the same IP address. We all carry our laptops, so as we go through our day, we get assigned different IP addresses from different base stations, right? And so these addresses get blacklisted, and then your IT department will have to go and delist them. Unless they do, you may encounter this type of service disruption. Okay, so again, this type of data arguably is scalable and global. Slightly less so. So if you want to get hold of this type of data, you have to subscribe. Sometimes it's free, sometimes you have to pay to these lists and get hold of the data. The difference here is these are actually explicit signs of botnet activity. So there is compromise. The nuance here is when it may not be the current device that's using the IP address because the dynamic churn in the address and machine association. Two is even though it is compromised, this is from our point of view, these do not count as material data breach, not exactly data breaches. So we are going to use these as features. Okay, so how do we perform this exercise to essentially understand organizational cyber risk? And this is, like I said, pre-LLM days. We use essentially a very standard supervised learning framework. Before we do that, we do have to aggregate the data. So the two types of data I just mentioned, they're host level data. So we have to aggregate them along organizational boundaries. And that, I have to say, generally is a very typical of this type of data exercise. It takes up probably 97% of our time. And then how do you, once you aggregate this type of data, how do you summarize? There are many different ways to summarize. One way is to simply do a count. So for instance, if you think about the malicious IP addresses, what you can do is you just basically tally up the total number of daily unique IP addresses seen to engage in malicious activities coming out of a single organization. So here what I'm showing is 3 different organizations over a 2-month period, and what you see. And what you see here is very different behavior, right? Now, some of this has to do with the size of the organization. So the one on the left is likely a very small company versus these two. But even among these two, you can see the difference. This is a company that may appear to be essentially not care about the volume of botnet activities that they have. This one they look like they're trying to do something, but not very effective. Okay. All right. So this is the type of input, and then you can extract any number of features. And what we did was basically a variety of first order and second order statistics. And then what you do is you feed this into again, like I said, standard supervised learning framework. You basically take features like this, okay? And these are labeled as there's no breach. So I forgot to say the feature data has to be paired with label data. And the label data is basically data breach reports. And then on this side, you have different sets of features that belong to organizations that have had data breaches. And then you feed them into training. We use this, our original study was done on using random forests that has since been replicated using regression and a number of other shallow learning models. Like I said, features and labels, and then you generate a classifier that can then take an unknown feature of a company with unknown status and essentially generate the likelihood of future breach. And that's the predictive framework. Okay, how well does it do? The output of this classifier, when we did random forest, it's a number. It's a number between 0 and 1, which is indicative of the likelihood of data breach. And to give you an idea how it works, and if you plot this output, predicted output, as a CDF, and you compare 2 population, one is a non-victim set, the other is a victim set, the wide separation immediately suggests that it has very useful information, right? So in a non-victim set, the predicted output is 80% of them has very low likelihood. Among the victim set, by contrast, a large 80% has high predicted risk. And then if you, in general, what you do is you adopt a threshold, you call one side high risk, the other side low risk. This allows you to turn your output into binary. Once you have binary, you get the standard measures. This is your false positive, this is your false negative, this is your true negative, this is your true positive, right? And then you can move where this threshold is. That allows you to basically plot this receiver operating curve, okay? Before I leave this, I'll just say what these points are. This was a prototype study we did back in 2015. This was OPM. This is the largest federal government's Office of Personnel Management back then. When each one of these happened, it was labeled, headlined as the largest breach at that point. And I think many of these we have already forgotten about because they have been essentially overshadowed by more recent breaches. This was Scottsdale's a major trading firm, T-Mobile breach, and T-Mobile has had quite a few after that. This is Experian, Anthem, and this is Penn State. Universities generally do not do very well because we have a very open network infrastructure in general. Okay, so this is basically, hopefully gives you some idea of what you can do with this type of data. I'm now going to get into, by the way, we have a fairly small group here, so feel free to raise your hand or type in a chat. I trust me here will help me see if you have any questions, feel free to jump in. So let me pause here. Any questions? All right. If not, let me go get into the 3 more recent studies. The first one is compressing the internet using a variational autoencoder. All right. So again, I'm going to go back to the scans, right? With this is the bread and butter. This is the data we're talking about. Now, if you look into what each scan record is, these are structured documents. They are essentially nested JSON documents that can contain thousands of data fields. And the structure is not fixed. It depends on how the host is configured. So here is a concrete example of what this data looked like. Okay, it's basically a spreadsheet. Okay, and a slightly better representation of this is actually a tree. Okay, different categories and how deep you can go down in each branch is device dependent. Sometimes you quickly stop because there's no response. You don't get that type of information. Sometimes you can go fairly deep down. And here I called out the HTTP because in my second study, that would be the main focus. Okay, so this is type of tree documents we have. When we started this exercise, the question we had in mind was, can we, okay, given that this is your data, these are the records, and we have millions and millions of these, can we extract low-dimensional numerical representations? Okay, so let me repeat that. So basically what we want is to turn each of these long record into a vector of numbers, if you like. Okay, numerical, not only we want to turn them into numbers, but we want that vector to be of low dimension, okay, lightweight. So that was the question. Why were we interested in that? Because once you turn things into numbers, you can engage with distance-based analysis. And this is not very different from what people have done with text analysis, right? Text to word to vec, for instance, you're mapping words into a Euclidean space. Okay, so this was the question we had. What did we do? So basically we did this back in 2017, 2018. Again, this was pre-LLM. So we basically did the most natural thing, which is to turn each of this record into a very, very long binary string to begin with, okay? And so we transformed each field, strings, you tokenize them, that includes headers, banners, and numbers, you bin them using one-hot encoding, and that includes things like latitude. This is kind of some semi-automated. There are things that went into fine-tuning this. For instance, we ignored sparse or irrelevant features and measurements. Some of this has to do with timestamps. Okay, so there's always a timestamp. Now, timestamp is not particularly relevant for what we're interested in doing. Okay, and so some of these things that you remove, and then we concatenate the extracted features, and we end up with 11,000 features. So here's some examples on how you do this type of processing, depending on the different data type and how you convert them. Okay, so then you end up with a very long binary vector, okay? And you can do this fairly fast. What do we do with the binary vector? This is what we wanted to do. It's essentially, again, what I said was that we want to turn this really long record into a very small fingerprint, if you like, a numerical representation. One of the tools that was available is called VAE, Variational Autoencoders. What this does is essentially through a iterative compression and decompression steps that tries to identify what's called a latent space and latent presentation. So the illustration here basically says, this is my original data, and you can view this as the binary vector. And you can actually do that sometimes losslessly if you can afford the size. Occasionally you have some encoding noise. And then you use this input to essentially train a pair of multi-layer perceptrons, okay? The first one is called an encoder. The second one is called a decoder. the encoder is essentially representing a conditional probability distribution of what the embedding would be given the input. And the second one is the reverse, is given the embedding Z, what the output might look like. So the second decoder is essentially a reconstruction step. So once you have trained this, what you get is from an output, you get a compressed version. Okay, and then the compressed version can go through the second block and give you a reconstruction. By comparing X and X hat is what you then use iteratively to simultaneously train both functions. Okay, so this is basically how this works. Our interest lies in discovering what this Z is. We want to know how good we can in identifying this latent space and latent variable, and whether that is a meaningful representation of your input X. Okay, now this type of model generally relies on that there exists essentially a latent space that's well described by Gaussian variables, okay, for this to work. Okay, so this is the underlying kind of architecture. So then you use the data I just described to train this. The first thing I want to show you is once you train this, again, you want to inspect whether the Z, the embedded, this latent variable is indeed well behaved. Okay, so we use the data that was available to us then between 2017 and 2018, and we use these records to train the VAE. And here's an illustration of what that latent variable Z looks like when projected onto a two-dimensional space. And what this tells us, it is actually pretty well, if you look at the kind of the approximate isotropic shape, I would say we have identified a reasonably well-behaved Gaussian random variable, essentially, distribution. Okay, so this is the first illustration. Now, how much does this Z latent variable capture in terms of information content, right? How effective is this compression? Turns out internet, I put it in quote because when I say internet, I mean these scans, right? These scanned records, it's highly compressible. Essentially, if I afford 10 dimensions, meaning this Z variable, I allow it to be a dimension 10 vector, then I can achieve less than 6% reconstruction error. So this tells us, and we have other ways to measure the error bound, essentially 10 numbers, right, numerically, is allowing us to capture, I would say, over 90% of the information content in that long record. Okay, and if you go up to 50%, you can reduce the error even more. Okay, so that's number one. Instead of giving you more numbers, I'm going to show you two things. The first is simply to visualize. Okay, what does this thing look like when we say this numerical embedding contains useful information? Okay, so the first thing is this picture. Remember, my Z is basically a sequence of numbers. It has no meaning, and that's the drawback of all these exercises. You kind of lose the interpretation. What you have is a set of numbers, and the set of numbers, the dimension of that vector is up to our control. I think this was generated from somewhere between 40 and 50 dimensions, but then you project that onto a two-dimensional space. Otherwise, I have no good way of rendering this. So this is projected from a higher dimension. Once you project it, so essentially these numbers don't really mean anything. It's just some low-dimensional Euclidean space. But then we start color coding these. We color code them using auxiliary information. We basically color code, so each host, each scan is essentially a point on the space. We color the points based on country of origin. And so what this is showing, the color is showing, the mere concentration of these colors basically shows that this numerical embedding is capturing very useful information. It shows the country, the concentration in origin, in location. This second one, we color code them in terms of server types, okay, machine types. And the concentration is also very interesting. This is basically what the embedding is able to capture. And the third one is in terms of whether the HTTPS certificate is trusted versus untrusted. And so this is kind of, I guess, more visual way of conveying to you that these fingerprints, contain good information. The second thing we did is basically to use this type of latent variables embedding, numerical embedding, to enable downstream application. So this is the overall framework. We call it host to vec, using the word, word to vec. What I have described to you in the previous slides is essentially this block. You basically convert these snapshots, scans into a vector, okay? Then you can use this vector, and I would say if you have the computational power, you obviously can always use the original binary vector to do this as well. To enable downstream applications, usually machine learning models and unsupervised or supervised, and to make detection as well as prediction. So one of the things we did was the detection and prediction, and the difference between these is just in terms of timing, how you line up your data, right? Whether you pretend you don't know the label and use the data prior to the label being discovered versus using feature and label information dated at the same time. To discover malicious hosts, these are basically phishing websites, okay? And so some of the nice features, as I listed here, they are fast and allows distance-based analysis. But one thing I want to highlight is this last bullet, which is when we compare this approach to content-based prediction and detection. Okay, content-based is what people do is they actually go to these malicious websites, analyze the content, including images and text, and try to automate this detection process. This method that I illustrate here actually outperforms that type of methods. And I think that's indicative of the fact that this type of compression actually allows us to capture more information. And sometimes image analysis is very hard to do because phishing websites essentially will steal, they'll copy high resolution logo and use it, which algorithm may not be able to tell the difference between the authentic one and the reproduced one. Okay, so this is my first case study. Let me pause here. Any questions?
Any question from the audience? Well, I do have a question. So it seems to me that you basically what you do is that you're basically extract information from the JSON file and learn an embedding from the JSON file and use the embedding to do the prediction. So and you also mentioned about it outperforms the content-based prediction. So does that mean that the JSON file itself contains more valuable information because your embedding is built on top of the JSON file instead of the original content inside the website?
So thank you for that question. So the key here, as I think you're alluding to, is the scan or the JSON file versus the actual what's on the web page convey very different information. The JSON file is telling us how the web server is configured. The content is basically what's the page that's currently being hosted there. And I will say, though, a priori, it can be hard to determine which one is better, right? Because you can say, if the page has already been hijacked, well, that ought to be more obvious, right? Whether it's a phishing site or not. On the other hand, you can also argue that the JSON file is essentially telling us how badly this thing is being configured, and that usually, because of the other exercises we have done, I can tell you that's highly correlated with essentially how likely a system can be breached, can be compromised. Because the configuration errors, even though they are not vulnerabilities directly themselves, they are highly correlated with how competent the system is being set up elsewhere. Does that answer your question? They're very different data. Yes. So this was basically an interesting observation. Okay, let me get into my next case study. Like I said, my first case study was done before LLM. So my next study is going to use exactly LLM. It's the same data, right? I put the same tree picture here. So the question is, well, now that we have these tools that allow us to directly analyze text, why don't we just use that? So skip this step of converting to binary vectors, right? What I have is a long, although I will say I wouldn't call this quite natural language, because it's a combination of very different things. Yes, it has words in them, but I will say some of these are very badly construed. But the idea is to directly apply more advanced tools to these data and generate embedding. Now, the good thing is that now we are not necessarily looking at so we have the ability to generate output that is also text-based, or let's just say not purely number-based, okay? So the same idea, right? Essentially, I'm mapping documents onto latent numerical space to capture, in this case, semantic information that we didn't have, okay? So we're going to use transformer-based LLMs to try to accomplish this. And this is actually a particularly suitable exercise because we have millions of these raw records. And for this study, I'm going to, I cannot quite see the right hand. Yeah, so I'm going to actually focus on just the HTTP banners. Okay, forget about the rest of the records. We're just going to focus on this and see whether we can generate embeddings or fingerprints. So device fingerprinting is a fairly large, actually, research area in the IoT space, right? So depending on what's being returned, do we have the ability to produce good fingerprints? So allow us to find out what's out there, who's out there, what are they doing? Okay. So that's the idea. All right. Now, using LLMs to generate embedding, this is basically what the pipeline looks like. This is, again, these are basically what the HTTP raw banners would look like. You use language models to generate embedding, okay, in a similar fashion, even though the algorithms are obviously very different. So basically, you turn them into this latent space numbers. Okay, you can control the dimension. And then we use a hierarchical clustering algorithm to cluster these numbers. And this is what I was saying. So once you turn things into numbers, all of a sudden you have at your disposal distance-based tools that you can use. So we use clustering to cluster these banners, these embeddings, into clusters. The reason is because you cannot, we're not generating fingerprints for each and every record, right? We want to generate good fingerprints for the same types of devices. And so then we use fingerprint generation to then create fingerprints for each cluster. So that's the pipeline. Okay. And so we trained LLM on 260 million banners from this essentially a similar database. We do actually collect our own measurement data as well, especially for my last case study. And then we used this embedding. The training gives us embeddings. Embedding leads to clusters, and then extract text-based fingerprints. Okay. There are a number of things that you like all data exercise. Again, it's easier said than done. There are plenty of things that you need to fine tune. One is we used a masked language model this type of model is very good in teasing out relations, semantic information. Okay. And that gets, so what you do is you randomly mask different regions of your data input and basically force the model to train the relation among different text and words. Okay. And this is usually a good starting point for this type of study. And then we also leveraged our domain knowledge. For instance, we know that these banners include a lot of dynamic section, timestamps again, sometimes random IDs. And these are not really germane to the study we want to do. As a matter of fact, if you want good device fingerprints, what you want is the static part of the banner, things that are invariant. And also, we know that snapshots from the same IP and ports are likely to correspond to the same type of product, if not exactly the same device. Okay. So for instance, how do we then detect dynamic portions of the banner? If you look at an example of a banner here, for instance, the parts that have been grayed out consists of two types of media. One is just the name of the field. So HTTP, server, MIME version. So these are never part of the, are not treated as an input to the training. So that's one. But then the second type of the gray fields is date information, time information, randomly generated ID, and so on. So we essentially train the model to detect these dynamic fields to remove them from the record. Okay, so we fine-tuned a masked language model to predict these sections and then use contrastive training to minimize and maximize the distance between records that belong to essentially the same port scan versus random pairs to improve consistency. Okay, so for instance, this is an illustration of if you look at how similar pairs that match, these belong to the same IP address versus randomly drawn two records. And this distance again shows us that the algorithm has a good ability to tease these out. Okay. So then we perform clustering using this hierarchical model I just mentioned. We can control the granularity. The one advantage is it generates multiple clusters simultaneously. And then we generate text-based fingerprints from these. And here you can see what we mean by text-based fingerprints. These are not exactly readable words, but it is, I think this is kind of commonly done in the community, and it is slightly more interpretable, I would say, than just numbers. Okay, so how well does this perform against, let's say, the state of the art is hand-curated fingerprints. And for those who are interested, you can check this out. I have a webpage here. And what we found is we're very successful at discovering the fingerprints between 90 to 99% coverage of what they have found. But we can also extract, I would say, novel fingerprints not captured by them. So here are some examples that our methodology is able to generate. So these are the expressions, regular expressions, essentially the fingerprints, and this is essentially readable descriptions of what we were able to, using this method, the types of devices we're able to identify. And because, again, these are essentially showed up as high density cluster identified from the numerical embedding, and these are then translated into these regular expressions. So there is some interpretability here. So this is my second case study. Any questions on that?
Maybe another question from my end. So
Yeah.
how scalable this approach is? There are potentially billions of, millions of the devices, right? And you're going to generate fingerprints for everybody. And yeah, just.
So I would say, like I said, we can control how big these clusters are. And I think I can go back to the numbers and see what is the, so here's the number, okay? So when we feed them the banners, these popped out 15K patterns from all the HTTP banners. So I would say this is a number that we, at this stage, we can comfortably handle. Yeah. Now, part of, I would say that the second layer to your question is, these are high density, but they may well contain actually 3 subcategories. Yep. So that's possible. And then there's further downstream processing one can probably do. Yeah.
Thank you.
All right. So let me get into my last case study, which is also the fastest. This is now on a different thing. It's again about scanning, but now we look at how we can make scanning itself more intelligent by using machine learning tools, right? So now you have heard plenty about these scans and IPv4 address space. The truth is, when you start doing the scanning, and you heard about if you have 1G bandwidth, you can cover the entire space in under an hour. The truth is, even that is vastly wasted, because only about 22% of this address space are live. Okay, meaning that there's something there, and that something there is accepting traffic. Okay, and even for those live hosts, their acceptance of probes remember they have thousands of ports that we probe. They only accept traffic on very few of those ports. So when you start scanning in an exhaustive fashion, most of your outgoing probes are essentially wasted time, energy, and bandwidth. Okay. Wouldn't it be nice to speed this up, make this more efficient by not sending our probes to things that are not live, right? And this is doable because there's a high, depending on which protocols and which ports you're talking about, there is cross-protocol correlation, okay? Meaning that if one service is not offered, sometimes you know with very high confidence another service is not offered. Okay, and this goes back to the device types, right? So for instance, here's an illustration of this this importance map. Each row and each column correspond to one protocol and their port number. What you see is these dark colors indicating how important it is for one port's response, that one port's response in their ability to predict the response from another port. Okay, and so we intentionally did not waste the diagonal space. Diagonals usually self-importance, but in this case, we actually use the diagonal color to indicate how well location and AS information contributes to our predicting whether that port is live, okay? And so there's basically a lot of information you utilize here. And so with this, what you can do is essentially we can train a model, an algorithm that looks at the correlation and use the response from past scan to predict future scan, and using that prediction to determine whether we should scan at all, we should send out a probe at all. Okay, so with this, you can uncover about 99% of active hosts for each probe at a probing rate of 14% compared to the exhaustive scan. So this can drastically lower the amount of resources you need. And this is kind of a simple schematic of how this works, right? So you basically do this sequentially. You go to a probe and you forecast whether you think it's going to be live. And then that determines whether you send or not. If you send, you look at the response and shuffle the remaining probes, determining not only which one to probe, but also the order in which you should probe them. And the latest version of this is actually trained using reinforcement learning. Okay, so here I reached the end of my presentation. I hope I conveyed to you that these scan information is very useful, and there are a lot more uses than I presented here. Some past work using shallow learning and more recent work using deep learning, and actually I would say using VAE, using large language model, using reinforcement learning, kind of just as a way to convey that there are a lot of opportunities there. What else can you do? I think there's a lot more one can do with this device fingerprinting as kind of a downstream application to do that. Once you can fingerprint them, there are other things you can do. I think there are more sophisticated risk quantification models this type of data can inform, and I'm sure there are plenty of others. For those of you in the audience, I would say I often try to take these opportunities to tell students that look at these deep learning models. It's oftentimes, I think, one feels overwhelmed by how much activity there is in image, in video, in text data. Even though I think there is just a huge space out there of very different types of data, depending on what application domain you're in, you're looking at very different data. And a lot of these data is actually structured, unlike image and video that's unstructured. And I think there are a lot of opportunities to engage with these data, engage with these tools to basically do what you want to do. Quick acknowledgement to the NSF and Cisco for supporting the work. A list of references here. The first three are the three case studies I presented. The last two are older exercise. That's the data breach prediction work that I mentioned in the beginning. With that, I want to thank you all for taking the time. I know I have not left too much time for questions, but we took care of a few. So
Thank you very much, Professor Liu, for the wonderful talk. Let's open the floor for the questions from the audience. Anybody from the audience who has questions?
I have one question.
Marty, it's you.
Hi, Miguel. First of all, very nice talk. Thank you very much. I have one question about the models that we are training. I want to know that how long do these models remain valid? So let's say that we train a model today with a bunch of data. I want to know that can we use this model, I don't know, next year to do some risk analysis or data breach prediction? How often we should update our models?
Yeah, so that's a very good question. So the industry practice, I'll tell you on the kind of the risk quantification and breach prediction, I think they generally retrain the model every 6 months. Okay, with the new data and new label. For the type of, so the VAE study, of course, is mostly a proof of concept, just to demonstrate that these scan records are very compressible. I don't think that conclusion is going to change very soon. For the LLM-based device fingerprints, I think it's a fascinating question. I think it would be worthwhile to actually do this over a period of time and then try to understand how much these fingerprints evolve. I'm sure they do because, vendors keep bringing on new devices, right? And the same types of device migrate. I mean, the software updates, hardware updates, they happen at a certain cadence. And so I guess my response is, I do think they need to be refreshed periodically. Exactly what that timescale is, I don't know. But I think for the purpose of research, and because this is highly automated, it perhaps makes sense to do this every 4 to 6 months and over a period of a few years, and that may be an interesting study. Does that answer your question, Mari?
Yep, thank you. I have one follow-up question. Also, for training these models, how much historical data we need? So do we need 1 year of data? Do we need 2 years of data if we want to have very accurate risk quantification or data breach prediction? How much data do we need? And yeah, how much historical data do we need?
So thank you for that question. So for I would say for the VAE, for the LLM work we did, they're actually all done on single snapshots. It's a one-time observation, right? Because that's a different type of study. It's basically looking at, here's the current state of the internet as I collected yesterday, and I'm going to run these exercises, and there's no history needed in this type of study. And there isn't necessarily a label per se, okay? Now, if you're talking about prediction and detection of malicious website, then we do need historical data for 2 reasons. One is you need to line them up with your label information. So for the data breach prediction we did, we went back not too far back into the past, depending on, we did a 2-week versus a 2-month parallel study to look at the efficacy. So in that case, the reason you need to reach into history is you want to make sure that your feature data predates your label data. That's the reason. Second reason why sometimes historical data is important is because we don't have enough label. And so you need to give yourself enough time so you actually have enough label information. If you limit yourself within this year, and okay, you have 50 labels, that's not good enough to do anything with. So I think understanding why you need that historical information is the starting point, and that can inform how far back you need to go.
Okay, sounds good. Yeah, thank you very much.
Thank
Very
you, Mari.
impressive.
Thank you.
Anybody else from the audience? You know, how many hours you put for labeling those data, right? Because I do see probably like hundreds of millions of data, entries there.
For which
I would
study?
imagine
For which study?
large language model one.
For large language model, that is mostly, so there is, yes, no. So okay. One frustrating part of the large language model is there's very limited ground truth data for the device fingerprints. That is the most frustrating thing. So I want to say what I'm showing you here is not exactly a comparison, accuracy comparison with ground truth label. It is really just about discovering what different types of devices are out there compared to the hand-curated database of fingerprints. So there's a difference there. Yeah, no, that's an excellent question. That is a persistent problem we have, and we have not actually done that. We know, so we have some, we know there are databases on hand-curated labels, but that's woefully inadequate. Yeah.
Yeah, I mean, this is really a timely, topic because large language model is the buzzword today, and it's really exciting to see, people from the networking community tries to leverage this language model for processing, human language or images or video data, and I would say, there are tons of data, as you mentioned, there are tons of data on the internet, right? That are publicly available, and most of them are structural data. I think the
Absolutely. Yeah.
study you showed, exhibits a great promise for this line of research. Yeah, they're really exciting. Yeah, this is kind of like free data. Everybody wants, this data to do research, and this is
They're out there. Yeah,
promising
they're
information.
out there. Yeah, and I think it's important for I know that you're not all students here, but for students here, it's important to know that face recognition is not the only application.
Yeah, finally, we have a source of data that is not images, not videos, not human languages. Wonderful. Yeah. So I think we are about time, and I want to thank Professor Mian Liu again for taking her time to give us a wonderful talk, a wonderful research area, pinpointed the future for using large language model for networking research. Very exciting. Want to thank her again, and I'll see you guys next semester then.
Thank you all. Thank you, me, for hosting this. Good to see everybody, and good to see Madi, Sharu, and I hope to see you all in June. I'm coming. Yeah.
Looking forward to that. Okay.
Thank
Thank you.
you. Yeah.
Bye, everybody.
Bye-bye.
Bye-bye.
Thank you. Bye bye.